Again, welcome back. And yes, it is very short and simple. Absolutely right. The survey. So, just to give a quick recap of what we have done in the last class, right? We looked at two different forms of state machines, right? Again, those two different forms differ based on how we represent the outputs, right? How we want to represent the outputs. Okay. So we talked about what is called a Mealy machine. And the Moore machine, right? Again, the only difference between these two is the way we represent the outputs. That's the only difference, really. Okay. Now let's. Oops, I did not intend to do that. Okay, are you able to see me? Okay, very good. All right. So Mealy and Moore. And in the last class, we also took the example of a particular application, right, in the design of sequence detectors. So, and we set out to design a circuit, a sequential circuit that can detect a simple sequence in the input bit stream 0, 1, 0, right? So basically you have a continuous stream of bits, okay, that are going into your sequential machine, one bit at a time, that is synchronized with the clock, okay? And what we want to do is you have the continuous stream of bits. I want to detect that particular sequence 0, 1, 0 in that bit. Every time I see the sequence, I would output my machine or my whatever I'm trying to design, the circuit should output a 1 every time I see the complete sequence 0, 1, 0, for example. In the last class, we implemented that. At least we looked at the design of this. Okay, we looked at the state diagram for this one particular circuit uh, based on the Mealy machine, right? So this is how we did it. So we have identified as 0 as a state that has we have assigned as 0 as a reset state, and now by now you know what that state really means, right? A reset state. We need to have a state called a reset state. So that's a state where I can go, reset, start looking for a new sequence, right? If I don't actually find the sequence. S1 as a state that has identified us that a first 0, because again we are trying to remember we're trying to detect a sequence 0, 1, 0 in the input stream. So I need to have a state that has identified that a 0 has occurred. The first 0 of the sequence has occurred. 0 has been identified in the sequence. The first 0. S2 has a state that a 0, 1 has been identified. Okay. So now, and then we set out to draw the state diagram, which basically looks something like this. Right? So we have S0. Again, I'm trying to design this as a Mealy machine. My Mealy machine, my output depends on the present state as well as the input. So my output is not necessarily synchronized with the clock unless my input is synchronized with the clock, right? So that's S1 and that's S2, okay? And then that's my reset state. When I'm in the reset, so this is how so you should have this in your notes. So I'm just going to go through this quickly. The output was 0, 1, 0, then S1, 0, 0 took me back to the same state. 1 took me to this state. S2. Yes, that's absolutely right. That's my X, that's my input X, that's my output Y. Okay. S2. So 0, 1, 0, because overlap sequences were allowed. So 0 would take me to S1 state, providing me with an output of 1 because I've identified the sequence, right? 0, 0, 1, 0. The sequence has been identified, so I output a 1 on my Y. And then when I'm S2 state, and if If 1 occurs, that means I have 0, 1, 1. That means it's not a sequence. I reset myself and start counting for and start looking for the next sequence. So that 1 gives me a. So I have the state diagram something like this for the Mealy machine. Okay. How does that change for a Moore machine? Again, recall that for a Moore machine, my outputs are synchronized with the clock. My outputs are functions of the state itself. In other words, my output is a function of only the present state. And because my states themselves are synchronized with the clock, my outputs are automatically synchronized with the clock. Okay. All right. And the way we represent, and again, going back to our previous lecture, the way we represent the outputs for a Moore machine is within the state itself, right? This is the representation. So if I'm in a 0 state, then my output is fixed to that state. As long as I'm in this state, let's say my output is 0. So that's the convention I would use to represent a Moore machine. So now let's actually start drawing a Moore machine, and then we'll implement both a Mealy and the Moore machine and look at the differences between the implementations. We should be and almost uh, most of the implementation is very identical except for the output, okay, as you may guess. All right. So in this case, again, I'll put S0 as a state, as a reset state, just like what we have done for the Mealy machine. S1 as a state that has identified a 0 has occurred in the input stream. S2 as a state that has identified a 0, 1 has occurred in the input stream. Now, unlike Moore machine, I need to have an explicit state, S3 here, which has identified that a 0, 1, 0 has occurred in the input stream. Why do I need this? Because my outputs are tied with the states. I need an explicit state that has identified the entire sequence. Okay. Now let's try to draw the state diagram for this one. Okay, again, S0. That's the reset state. I have not identified any sequence yet. So my output here, let's say my output is indicated by Y. My Y is 0. Okay. So as long as I'm in S0 state, my output is basically 0. Okay. Now so let's say I'm in S0 state. In the input stream, the first bit I encounter is a 0. What should be my state transition? Should I remain in the same state? Should I move to the next state? Transition to S1. Again, I have not identified the entire sequence, so my output is still 0. So x equal to 0 took me to the S1 state. What about x equal to 1? If I'm in S0 state, x equal to 1 is the first bit I encounter. I remain in the same state, right? Because 1 is not the first bit of my sequence to be detected. So I remain in the same state. So I reset myself and start looking for the next bit. Okay, now I'm in the S1 state. That means I've identified that the first 0 has occurred in my input stream. And another 0 occurs. So I'm in S1 state. My input now is x equal to 0 again. What should be my state transition? Should I remain in the same state? Should I move on to the next state or a different state? So it's something like x equal to 0 took me here. Another 0 happens when I'm in this state. And similar to what we have here, right? I discard this and look at this, the new 0, as the potential start of an actual sequence. Right? So I remain in the same state and start looking at this 0 as the start of my sequence, potential sequence. All right. What about x equal to 1? X equal to 1, that means I've identified a 0, 1 has occurred in my sequence, which is indicated by this 2 state. So I move on to this 2 state. I have not identified the entire sequence yet, so the output is still 0. Okay? So that's x equals 1. Okay. So I'm done with S1. I move on to S2 state. That means the fact that I'm in S2 state means that I have already identified 0, 1 has occurred in the input stream. That means I've identified these two bits of my sequence. Okay. Now I'm in S2 state. Let's say 0 occurs when I'm in S2 state. What should be my state transition now? Should I remain in the same state? Transition to S1. Okay. That's a possibility. But wait a minute. I have identified the sequence now, right? I have identified the sequence 0, 1 in my input stream got me to S2 state. Another 0, that means I have identified 0, 1, 0 in my input stream. That means my output has to be a 1. However, I cannot do that here, right? Because my S1 state, as long as I'm in the S1 state, my output is 0. My output is tied with the state here. Unlike the Mealy machine, my Moore machine, my outputs are tied with the state, right? That's why I have a new state here, S3 for the Moore machine, where it's designated as a state that has identified the entire sequence, right? 0, 1, 0. So that's why this would basically transition to S3 state, where I have identified the sequence x equal to 0. Okay, does that make sense? All right. Now I'm in this state. That means I have identified 0, 1 in my input stream. X equal to 1 occurs now. What should be my state transition? That means I have something like 0, 1, 1 in my input stream. Where should I transition to now? When I'm in the S2 state, and when I'm in this state, x equal to 1 occurs in my input stream. To S0, right? Because that's a reset state. When I'm in S2 state, that means 0, 1 has already been identified. Now the next input is 1. 0, 1, 1. It's not my sequence I want to detect, right? And I reset and start counting for the next bits and start looking for the next bits, right? So that's why I reset. X equals 1 takes me to the reset state. Okay, so I'm done with the S2 state now. Now let's move on to the S3 state. S3 state is a state that has identified that a 0, 1, 0 has occurred in the input stream. So that the entire sequence has been identified. Okay. All right. Now, so the fact that I'm in S3 state, that means 0, 1, 0 has been identified. And let's say the next subsequent bit is 0. All right. So what should be my state transition now from S3 state with x equal to 0, with a new x equal to 0? S1. Okay. S1. Again, I need to emphasize, I need to make sure that I say that overlapping sequences are allowed in this case. Just like what we have seen for this, just to be consistent, let's say that overlapping sequences are allowed. What does that mean? That means that means if I have something like this, I count that as a sequence, I count this as a sequence as well. Okay. So just wanted to remind you guys that aspect. Okay, so now I have 0, 1, 0. The new input is 0. Okay, so you're right. So I can start counting this as the new start of my sequence, or the start of a new sequence, right? The 0 could be the start of a new sequence. So yes, I would transition to x equal to S1 state. That's correct. All right. The other possibility is I have 0, 1, 0. I've been identified because I'm in the S3 state. The input now is a 1. Okay. The other possibility is, of course, for the input to be a 1. Now, what should be my state transition now? S2. Very good. Very good. Because this particular, because overlapping sequences are allowed, this could be the uh, beginning of a next sequence. I've already identified 0, 1 of the next overlap sequence, and the state that has identified this 0, 1 is nothing but S2, right? S2 is the one. So that means I should transition to S2 with x equals 4. And that's it. So that's my Moore state machine. That's my Mealy state machine. Both of them doing the exact same purpose, right? Identifying a particular sequence, the same sequence. Of course, in this Moore machine, I need to have an additional state to account for the fact that my outputs are tagged, are coupled with state itself. So I need to have an explicit state with an explicit output of 1. Okay. All right. Let me take a pause here. Let me see if you have any questions. Does that make sense? Okay, so S1 goes back to itself when there is a 0. S1, yes, that's correct. So now you can actually go through this state diagram with any arbitrary sequence. So this is a good idea that you can use to validate your state diagram. Okay, so you can choose any arbitrary sequence. Let's say 0, 0, 1, 0, 1, 1, 0, 0, and so on. Okay, and run it through your state diagram. Right. So I have 0, 0. Let's say I'm in S0 state. 0 takes me to S1 state. Another 0 occurred. Again, so I remain in the same state, counting this 0 as the potential start of a new of the actual sequence, right? Okay, I remain in the same state. So here I can represent my state transitions as from S0 to S1. I remain in the same state S1. Then when I'm in S1 state, a 1 occurs that took me to S2 state, right? And when I'm in S2 state, a 0 occurs that takes me to S3 state. And S3 state is a state that outputs a value of 1, right? So that's a 1. And another 1 on S3, 1 on S3, where does it take me to? The 1 on S3 takes me to S2 state. Okay, this corresponds to S2. 0 on S2 state takes me back to S3 state, really. Okay, let's not get confused here. Let me 0, 0, 1, 1, 0, 1, 1, 0. Okay, so let's say this is my sequence. I'm going from S0 to S1. I remain in S1, go to S2, go to S3. I've identified a sequence. Output is a 1. And then when I'm in S3 state, 1 occurs. 1 takes me to S2 state. So 0, 1. When I'm in S2 state, another 1 occurs, takes me to S0 state because that's a reset state. I have not identified any sequence. I reset. Then 0 occurs again on when I'm in S0 state, takes me to S1 state, and so on. So you can run the sequence, validate it by running this through your state diagram, and make sure that it actually works. Does that help, Fletcher? Is that what you're trying to say? So S1 goes back to itself when there is a 0. That's correct, because I discard the previous 0, start counting the new 0 as the start of my potential sequence. Does that make sense? Okay. Now, when you are at S2 and you have a 0, okay, what is the reason for why it cannot go back to S1 and forward to S3 with overlapping sequences? So when you are at S2 and you have a 0, 0, okay. Okay, what is S2 state? What is it why you cannot go back to S1? Okay, because let's say I'm in S2 state. What brings me to S2 state? This particular sequence bring me in the input stream brings me to S2 state, right? If I have identified a 0, 1 in my input stream, that brings me to S2 state. Okay. Now 0, 1 in the input stream brings me to S2 state. Another 0 occurs. Now that is the sequence I want to detect, right? And I have detected the sequence, right? And that's why I go back here. I go to the S3 state, a new state that is designated as the entire sequence has been detected. Now the question was, why cannot do this? Why cannot I do this like I've done in the Mealy type, right? Here I can do this because my outputs are not functions of the state, but my outputs are a function of state and the input. I have the luxury whereby I don't have to have an additional state here, okay? And I can simply represent the output as a 1 because uh, because in the Mealy type I have the output as a function of both the state and the input. So I can do this. But in this case, I have to have an state with an explicit output of 1. Because my outputs are coupled with the state itself, I have to have an additional state defined in this way, because 0, 1, 0 is the sequence I want to detect. I need to have a state that has detected the entire sequence so that I can have the output for that particular state as a 1. So that's why I have this transition and not this one. And overlapping is still works, right? Because because of the way I have this transition happening here. So I have 0, 1, 0. Let's say another 1 happens. Okay. Because and then let's say this is one sequence, this is one sequence, right? 0, 1, 0 takes me to S3 state. If I have a 0, 1, 0 in my input stream, that took me to S3 state. Now a 1 occurs when I'm in the S3 state. A 1 occurs, that means that takes me to S2 state, which has identified a 0, 1 has occurred, right? That's why I have this transition. And when I'm in S2 state, a 0 occurs. That takes me back to S3 state. So that's S3 state, S2. That takes me back to S3 state with an output of 1. So overlapping still works in this case by the way we have drawn these transitions. Does that make sense, Kyle? Are you with me? Okay. All right. So let's try to implement this. Okay. Um, I wanted to show. Okay. So let's actually implement the Mealy type first, and then the Moore type. All right. Okay. Now, how many state variables for the Mealy type should I be using? I have 3 states. State variables, number of state variables. What do you think? 2, right? I need basically 2 state variables. I have 3 states. Each state has to be encoded with a unique binary code. So let me say I encode this as 0, 0, 0, 1, 1, 0. Okay. 2 state variables, A and B. Let me draw the state state table here. So that's my present inputs. present state, I'm sorry, that's the present state. Then comes the inputs, next state, and the output. Okay. I've encoded my states. My state variables are two. Let me call them A and B. Input is X. Output is, next state is A plus B plus. And output is Y. Okay. All right. And now let's look at all possible combinations. Okay. What am I trying to design here? I'm trying to design. Again, I go back to my general block diagram. That's my input X. This is a combinational block. My state variables, present state, next state, going to these two flip-flops. In this case, I'm using a D flip-flop. Let me call it DA, DB, QA, QB. And basically, this is what I'm trying to implement. Of course, I have the clock. I assume that the clock is internally connected to both A and B flip-flops. Okay. And of course, I have the Y, the output, Y here. So this combinational block is what I'm trying to implement. Now, if I look at the level 0 diagram, I've identified that I have three inputs. These are my inputs to the block. I have three outputs. These are the outputs for the block. That's it. It basically boils down to the design of the combinational circuit. So let's do that. I look at all possible combinations for the inputs, because it's basically the truth table I'm writing here. Okay, and I go back to the state diagram here to populate this table. Okay, again, remember that 0, 0 corresponds to a 0 state, 0, 1 is S1, 1, 0 is S2. I have not defined a state called 1, 1. Okay, I don't have that state here. So I don't have to worry about that. Okay, so 0, 0, 0, 0, 0, 0 takes me to S1 state, which is designated as 0, 1. Output is 0. 0, 0, 1, 0, 0, 1 takes me back to the same state. Output is still 0. 0, 1, 0, 0, 1, 0 takes me back to the same state. Output is still 0. 0, 1, 1 takes me to S2 state, which is designated as 1, 0. Output is still 0. Is that right? Yeah. And then I'm done with that. And then I'm 1, 0. 0 takes me back to the S1 state, which is 0, 1, with an output of 1. Right? An output of 1. 1, 0, 0 takes me, oh, I'm sorry, let's see. Yeah, 1, 0, 1 takes me to S0 state with an output of 0. 1, 1, I don't have a state called 1, 1. So I can just have them as no one cares. And now I need to solve for A plus, B plus, and Y. I don't have to have this anymore because this information is now represented in the truth table. So what is A plus? I can already see that A plus is A prime bx, right? A plus, which is nothing but dA, is A prime bx, right? That's the only one I have. So what about B plus? I can see that B plus is x prime, right? B plus x. X is 0, B plus is 1, x is 1, B plus is 0, 0, 1, 1, 0, 0, 1, and so on. 1, 0, and so on. So I can say my B plus is simply x prime. and y. Y is 1 only for this particular combination, which is 1, 0, 0. So that means A, B prime, X prime. A, B prime, X prime. I could have done it with the K-maps. That would have given me the same answer. But I just looked at the truth table in this case to derive those answers. Okay? All right. And that's it. So if I were to implement this, then my circuit would look something like this, right? So I have dA, dB, QA, QB. That's the clock. Okay. A plus, which is dA, is A prime. What is A prime? Again, remember that A prime or A is nothing but QA, right? A prime BX. B is QB. A prime B, and let's call this X, and that's my dA, or which is nothing but A plus. Okay. B plus is simply X prime. So I can just take that. That's B plus, which is dB, which is simply X prime. So it's very handy when I have this diagram. It becomes very handy when you're trying to implement that circuit. And finally, we have Y, which is A B prime X prime, which is A. Again, A is nothing but QA. QA is that. So Y is A B prime X prime. A B prime. B is nothing but QB. A B prime X prime. And that's my Y. Of course, I could have done everything here, but I just wanted to show it a little bit more clearly there. 6 prime, right? 6 prime. Yes, that's right. AB prime X prime. That's correct. And that's my Y. And that's it. So that's how you would have implemented the sequence detector for 0, 1, 0. Okay. Now let's quickly do that, the similar exercise for the Moore machine. Okay. And that will complete our discussion here. For the Moore machine or for the Mealy machine, the general block diagram does not change. This is basically the same. The general block diagram does not change. Of course, the internal circuitry does change, but for any state machine, this is the general block diagram. So make sure that you remember that. All right. So let's do the Moore machine. Okay. Again, I need to know what the state diagram for that was. So this would change. For a Moore machine, I have 4 states. So that's why I could call this as 3 state. Okay. So let me quickly put that down here. It's 0, or Y was 0. S1, Y is 0. S2, Y is 0. S3, Y is 0. Okay. So 0 takes me there. X equals 1. 0, 1. 1 takes me here. 0, 0 takes me back to the same state. Then I'm in here. 0 takes me to S3 state, 0, 1, 0 is detected. Oh, I'm sorry, this is 1. Because I've detected the entire sequence. And 0, 1, 1 takes me to a 0 state. Okay, so I'm done with this. 0, 1, 0, 0. 0, 1, 0, 0 takes me to S1 state. And 0, 1, 0, 1 takes me to S2 state. So that was the state diagram for that. And now let's put down the information from the state diagram. Okay, so 0, 0, 0. Again, S0 is designated as 0, 0. S1 as 0, 1. 1, 0, 1, 1. That's how I've encoded those each states. So 0, 0, 0 takes me to S1 state, which is 0, 1. Output of 0. 0, 0, 1. 0, 0, 1 takes me back to the same state. Output is still 0. 0, 1, 0. 0, 1, 0 takes me back to the same state. Output is 0. 0, 1, 1. 0, 1, 1 takes me to S2 state, which is 1, 0. Output is still 0. 1, 0, 0. 1, 0, 0 takes me to S3 state. Output is still 0. 1, 0, yeah, 1, 0, 0, okay. 1, 0, 1 takes me to S0 state. Output is 0. 1, 1, 0. 1, 1, 0 takes me to S1 state.
Professor?
Yep.
Professor?
Yes.
So shouldn't for uh, the 100 state, shouldn't the output be Y because it's in the S3 state? The output should be 1.
That's a good point. Now, the way we have defined, if you look at this, if I'm in this state in the present instance, then my output is a 1. So I have to be in that present state for my output to be a 1. That means if I'm in this state, then my output is tied to this state, right? That's my present state. So my output is a 1. Make sense? Then I have 1, 1. Again, my output is basically a function of the state. 1, 1, 1. 1, 1, 1 takes me to S1 state. 0, 1. Sorry. Is that right? 0, S1, wow, sorry, S2 state, 1, 0. 1, 0. And the output is 1 because I'm in this state. As long as I'm in this state, my output is tied to that state. Okay? So very important. That's a very important point that you brought up. And there should not be any confusion here. My outputs are tied to the present state. As long as I'm in that particular state, my output is a 1. And my output is, how I defined, right? So as long as I'm in this particular state, my output is a 0. As long as I'm in this state, output is a 1. Okay? And that's it. So what is A plus? Can we directly do it from here? Maybe not. Yeah, we may have to. Yeah. Zero, 1, 1, 1, 0, 0. Give me a 1 for A plus. So it's A prime Bx plus A B prime X prime plus that. Okay. B plus 1, 0, 1, 0, 1, 0, 1, 0. So that's B plus is still X here. So that's good. B plus is X. A plus, I need to find out what A plus is. Y I can easily say because my Y is a function of S3 state. S3 state, so every time I'm in S3 state, B plus X prime, that's correct. Y should be basically AB because it's a function of only the present state. And I get an output of 1 only for this combination, right? So y is AB. What is A plus? What is A plus? Let me see. This time I will not use the K map. I will just use the algebraic simplification. But I'll just have 3 1s. So that's A prime bx. That's A prime bx plus A b prime x prime plus abx. Can I simplify it? I can. So that should be. So I can eliminate A from here. That's bx plus A prime b prime x prime.
Professor, it's just AB prime X.
A b prime x. Did you do it with the? Is that right? A b prime x.
You added an A prime.
A b prime x. For which one? Oh, okay. Sorry. A b prime. A b prime x prime. Right? Yeah. Okay. So that's bx plus a b prime x prime. Can I simplify it any further? I guess that's it. So this is what I have for a plus. Okay. Now you should be knowing how to get back to this because it's nothing but we're designing this, right? I got my y, ab. What is ab again? This one. Y is simply ab, which is nothing but qa qb. Same thing. B plus is x prime. Okay. Or let me put it this way. Okay. And finally, y is a little bit more complicated to put in there, but you know how to do the connections, I hope. All right, so that's it. So that's how you would design a Mealy machine. That's how you design a Moore machine. That's the difference between them. As you can see, the implementation is almost similar, except for the output. The output only depends on present state. Okay. Any questions here before I move on? Are you guys with me until this point? So it's very important that you practice the state machines, implementation of the state machines. We have many examples on the homework. We have done a few examples in the class. See if you can do it by yourself. And in the homework, you have a little bit more involved example where you're trying to detect two sequences. One, I think it's 1001 or 010, something like that. Okay. So when either of these sequence occurs in the input stream, then your output should be a 1. So that's a little bit more involved and more fun. Okay, you may have to have more number of states than just 3 or 4. Okay, but it's a fun problem. I hope you'll be able to get it. All right. How are you feeling so far with the state machines, the concepts on state machines? Any place or any concept that can be clarified at this time? Okay. Now, as I mentioned before, I can implement a state machine. In all the implementation examples that we have taken so far, we have used a D flip-flop. Again, the characteristics of a D flip-flop, as you can see, for any D flip-flop, the output follows the input. Right? With each new clock transition, the output follows the input. Right? And that's why we really did not have to do anything extra here. Right? my AB are applied as inputs, or my A plus and B plus are the inputs to the D flip-flop. And with each new clock transition, again A plus and B plus represents the future state, and with the movement of the clock, the future state becomes the present state, right? And that's how we gather feedback. And because A plus follows A, B plus follows B, I didn't have to do anything extra here for the D flip-flop implementation. Now, if I were to implement the same circuit using a JK flip-flop, how would I do this? Okay, I don't need this anymore. First of all, let's look at how the block diagram changes when I want to implement this using a JK flip-flop. Let's start with that. So in this case, what I will have is again a combinational block, right, that takes in the input X. That's my present state, A and B. My future state is stored in the flip-flop for one clock cycle. And in this case, I'm trying to implement using a JK flip-flop. Again, the number of flip-flops I will be using would be equal to the number of state variables I'll be using in my block diagram or in my circuit. So in this case, I'll be again using two flip-flops, call it J and KA, JB and KB. That's going to be QA, QB. Okay. Now that's my present state that computes something, or that should be basically give me the next state. Okay. And in the future, or in the next clock transition, the future state becomes the present state, and that's why we feature this feedback. So unlike the other example where we use a D flip-flop, here I have four inputs for this flip-flop, right? For these two flip-flops, I have JA, KA, JB, and KB inputs. That means for this combinational block, I have to compute, of course, Y, the output, and JA, KA, the inputs to the first flip-flop, the inputs to the second flip-flop, okay, whatever that is. I'm sorry, we can call it that K plus. Okay, and of course, these are connected with the clock. All right. Now, my circuit changes, the block diagram for the circuit changes slightly. Instead of A plus and B plus, because a D flip-flop would only have one input, that's why I just did A plus and B plus. Now I have two inputs for each flip-flop. That makes it four inputs. Okay. And let's say I have a state transition something like this. Let's say this is my present state. Okay. And this is my next state. Okay. Let's say I'm in a state 0, 0. And in the next clock transition, I have to transition to a state called 0, 1. Okay. All right. Now that means in the next clock transition, this future state becomes my present state, right? The future state becomes my present state in the next clock transition. So what it indicates is if I have 0, 0 now, if I'm applying 0, 0 here, okay, what should be applied on JA, KA, JB, and KB here so that I get a value of 0, 1 here being applied here in the next clock transition. In the case of a D flip-flop, it was clear. It was trivial because the output simply followed the input. So whatever I apply here, in the next clock transition, I would be basically getting that value here. But for a JK flip-flop, it's not that simple. It's not that obvious here because I need to apply some values here so that in the next clock transition, I get this transition. So the question is, what should I be applying here? Or how should I determine what should be applied here so that I get the right next state values? Okay, so let me take a pause and let me see if you have any questions here. Does it make sense where I'm heading to? What the problem statement is? Eric? Are you with me until this point? Okay, how about the others? Joshua, Matthew, Samuel, Vikas. Okay, so can I move forward? All right. So again, the problem statement, or what we're trying to do here is, how should I determine what should be applied here so that I get the right state transition from one state to the next? Oh, I'm sorry to hear that. Okay. All right. So for that, let's actually start with the characteristic table for a JK flip-flop. That should be our starting point. Okay. For the characteristic table, basically you have J and K, right? Those are the two inputs, and then QT plus 1. Or what happens when I apply some values on J and K and then wait for the next active edge? What happens in the next active edge, right? So we already know this. These are all possibilities for my J and K inputs. We know that when I apply 0, 0, that corresponds to the memory state. So whatever was there before, that will continue to be there. 0, 1 corresponds to the reset state. 1, 0 corresponded to the set state. And finally, 1, 1 corresponded to the toggle state. That's what the characteristic table for a JK flip-flop. Again, that's not, I mean, that's useful, but it does not give me the entire picture, right? What I want to know is, for Q to Q plus QT plus 1 transition, this is what I want to know. For a particular transition, so I'm kind of going in the reverse direction here. What should be applied on J and K to get this transition? Okay. Here, the characteristic table, what it gives is, if I apply these values, I get this as the next on the next pulse. Okay. So to get that information, what I will do now is I will redraw this table in a slightly different fashion. What I will do is I will say JK Q of t, and then Q t plus 1. So these are my inputs. In the present instance, that's going to be the output in the next clock instance. And let's look at all possible combinations. Okay, I'm just rewriting this characteristic table in a slightly different modified fashion, just to make things more obvious, if you will. All right, let's look at the first row. I'm applying a value of 0, 0 on my J and K. My present output is 0. So what should be my next, on the next clock transition, what should be my output for the JK flip-flop, represented by QT plus 1? J and K are both zeros. My present output for the JK flip-flop is 0. In the next clock transition, we have the characteristic table, right? That should be 0. That's the memory state. So this value remains. What about 0, 0, 1? Same thing. That should be 1. That's the memory state. Whatever value is there before or in the present state remains in the next state, because that corresponds to 0, 0 corresponds to the memory state for JK flip-flop. 0, 1, 0. Apply value of 0, 1 on my J and K inputs. Irrespective of what I have in the present output, the output is going to be updated to 0, right? Because that's the reset state. So 0, 1 on J and K will basically reset in the next clock transition. So irrespective of what you have as the present output, that's going to get reset. 1, 0 on my J and K. That's the reset. That's the set. 1, 0 sets my output. So irrespective of what you have in the present instance, with the next clock with the next active edge, the output is going to be set 1 0 again, that's going to be set. And finally 1 1 corresponds to the toggle state, right? So whatever I have in the current instance, that's going to get toggled. So if I have 0, that's going to become 1. If I have 1 in the present instance, that's going to get a 0. So that's going to turn into a 0. All right? So why did I write this in this way? The reason is, what I'm really looking at is for these transitions. For these transitions to occur, what should I be applying on J and K? So I will rewrite this table, and this particular table now is called the excitation table for the flip-flop. This table is nothing but the characteristic table written in a slightly different way to make it more obvious for these transitions. And this table is now going to help us with the excitation table. So what does the excitation table indicate? In this case, I want these transitions to occur. So Qt to Qt plus 1 transition to occur. And for this transition to occur, what should be applied on J and K? Okay. So again, let's look at all possible combinations: 0 0, 0 1, 1 0, 1 1. Okay. What does this mean? Let's look at the first row. For a Qt, if in my present instance I have a 0 on the output of the flip-flop, in the next active edge, I should have another 0. My Qt plus 1, the output should still be 0 in the next active edge. Now for this transition to occur, what should I apply in J and K so that this transition occurs in the next active edge? So again, I go back to this table. Look at these transitions or the instances of those transitions. So in this case, I can see that this is one instance where the transition is occurring, right? 0 to 0, 0 to 0 transition. Another transition is here. Okay, I have two possibilities. 0 to 0, one of the possibility is here, 0 to 0 transition, 0 to 0 transition. Okay, so you're partly right. 0 0 can get you there. So now let's look at what values were applied on J and K to get those transitions. Okay, so 0 to 0 transition, I need to apply a value of 0 0. That's one possibility. Or I can apply a value of 0 1 on J and K to get this transition. Right? I have two instances of that. I look at what values were applied on J and K from this table, either this or this. So in other words, as long as I have a J of 0, if I apply a value of 0 on my J, K doesn't matter because K of 0 gave me 0 to 0 transition. In this case, I have a K of 1. I said absolutely right. So K will be a don't care. I don't have to care about K because as long as J is 0, I will get this transition. Okay, now let's go to the next possibility, 0 to 1 transition. Again, I go back to this table. I will see that I have two possibilities for that, or two instances for that. 0 to 1, let's see, I have one instance here, and where is the other one? Here. Yeah. Again, I do the same thing. I go to this. So for this transition, one of the possibility was I apply J as 1, K is 0. The other possibility was J as 1, K is 1. So as long as J is 1, irrespective of K, I will get that transition. Okay, that's good. Now 1 0. Same thing, do the same exercise. I have one instance here for 1 0, another instance here. So to get 1 0 transition, J was 0, K was 1. That's one instance. Another instance, J was 1, K was 1. Right. So in other words, J don't care, K is 1. Okay. And finally for 1 1, 1 1 is 0 0, J and K both zeros, or J is 1, K is 0. In other words, K is 0, J is don't care. Right? And that's it. So now I know for these transitions to occur, what I should be applying on my J and K. All right. So now how does that relate to my state table? I don't have, of course, my A plus B plus represents the next state. So what I will be doing now is when I want to implement a state diagram or a state machine using the K-maps, I would be redrawing my state table slightly differently. Okay. Are you with me until this point? How we derive the excitation table for the flip-flop. So this is the format you will use. This is the methodology that you will be using to deriving the excitation table for any flip-flop. Let's say in the exam, for example, I come up with a new kind of a flip-flop. I give you the characteristic table for that flip-flop, and I ask you to derive the corresponding excitation table for that flip-flop. What should be doing? What should you be doing? You basically follow this. So that is given. You know that is given. You express your characteristic table in this format that shows explicitly the transitions, right? And then from this table, you basically obtain the excitation table, which shows you for these transitions in the outputs with each clock pulse, what should be the values applied on the inputs. Okay, so you'll be following the exact same methodology. All right, so this is very important that you take a note of that. All right, so now, we're done with this. That's my excitation table. Now let's try to implement the same circuit, but this time with um, with the aid of JK flip flop. Okay, so that's my present state. So that the way I would write it is something like this. So that's my present state. Input. Next state. And now I have 4 different outputs, right? You remember we had JA. I need to apply. I need to know what should be applied on JA, KA, JB, KB, and of course you have the output. Y. Okay. All right. So present state 0, 0. Input is X here, 0. The next state, A plus B plus. Okay, let me actually write it down. AB, X, A plus B plus was 0, 1. All right. And the output, okay, let's not worry about the output because the output, the implementation of the output does not change. 0, 0, 1 was 0, 0. 0, 1, 0 was 0, 1, and so on. Okay. So let me actually do it for these instances. Okay. Now for this transition A to A plus of 0 to 0, what should be applied on JA and KA, right? Ultimately, I need to find out because this JA, KA, JB, KB are the outputs of my combinational block. I need to find out these values, right? So for 0 to 0 transition, 0 to 0 transition, A to A plus, which corresponds to 0 to 0, my JA should be 0, KA should be X. Now for B, let's do the same thing for B. This transition is governed by the values you apply on JB and KB, right? For 0 to 1 transition here, B to B plus, 0 to 1, 0 to 1, I need to be applying 1x on my JB and KB. Likewise, 0 to 0 was 0x, 0 to 0 again is 0x, 0 to 0 is 0x, 1 to 1 now, B going from 1 to B plus as 1, 1 to 1 is x0, x0. And you basically populate this table. My JA, KA, JB, KB are outputs of the combinational block, which are functions of A, B, and X, right? So you compute them as the functions of A, B, and X, and you implement the circuit. That's how I would basically implement sequential circuits. The same principle, nothing has changed, okay, by using a different flip-flop, in this case, in this case, a JK flip-flop. Okay. And you will see that when I use a JK flip-flop compared to a D flip-flop, of course, when you're trying to compute it, it's more work on the paper. But in terms of implementation, in terms of circuit complexity, it's going to be reducing much more. You don't have to use as many external gates as you would have used when you're trying to implement that using a D flip-flop. Okay? So that's the advantage of using JK flip-flop. Of course, it's more work on our end, on the designers. However, in terms of power consumption and other aspects, complexity and size of the circuit itself, it's going to be less complex. All right, guys. So that's it. So we have 3 more minutes. What I would like you guys to do is, I would like you to go to the survey link. Please make sure that each one of you complete the survey. This survey, in addition to the survey that was previously posted, that's more to do with the teaching techniques itself. But this one is more towards ABET, and so I would request that you do that. Okay. So with that, I'll end this class and the course.